Today we'll be attacking special right triangles. Now, special right triangles are going to be important in geometry class, but they're going to come with you in every class after this, Algebra 2, Pre-Calc, so on and so forth. So if you want to have less stress and do better in future math classes, know your special right triangles. I cannot give you better advice than that. Know these by heart. You want to increase your ACT score by 3 points? I can't guarantee it, but it will definitely help on the timing because we're not looking for you to use the Pythagorean theorem every single time. We want you to use the conveniences of 30, 60, 90s, and 45, 45, 90 right triangles, which we're going to talk about. So if you want to be on the secret side of math where you do less work because mathematicians are really smart, lazy people, know your special right triangles. The first one we're going to deal with is a 30, 60, 90 triangle. And I'm actually going to go through the proof of that 30, 60, 90 triangle. What I have right here is an equilateral triangle. So each of the sides is 2. In an equilateral triangle, all the angles are 60 degrees. But I drew this diagonal, this reflection line here. That means I cut it or bisected it into two 30-degree angles. Now I have a triangle that has a 30, a 60, and a 90-degree angle. From here, when I cut that in half, I actually have a side now of 1 and 1. Right there is our first nice relationship about 30, 60, 90s. This side is my short side. Why it's my short side is it's across from the 30-degree angle. The shortest side is always across from the shortest angle. That short side is always going to be half the hypotenuse, or if I double it, I get my hypotenuse. But this x length is what we really want to attack now. So I can use the Pythagorean theorem. I get 1 squared plus x squared equals 2 squared. So 1 plus x squared equals 4. I subtract the 1 to the other side, and it says x squared equals 3. I take the square root of both sides, and x equals the square root of 3. That side right there, then, its length is the square root of 3. It's easy as 1, 2, 3. 1, 2, 3. Oh, well, it's actually 1, 2, square root of 3, but those are the ratios of a 30, 60, 90. Now, all 30, 60, 90 triangles are similar. They're similar because of angle, angle. So, to generalize this, I can actually use these ratios no matter how big the triangle is. So, if my short leg is x, we said 1, the hypotenuse is going to be 2 times bigger, 1, 2, and then x times the square root of 3. It's going to be 3 or root 3 times bigger than this short leg. But these work all the time. So if I have a triangle, let's say the side length is 5 for the short across from the 30. I guess all they have to give me is one angle. This right triangle, I know this is 5. This is 5 root 3, and that's 10. We don't want you to use SOHCAHTOA. We don't want you to use any of that stuff. We just want you to fill in the sides and go. That's the convenience. So I want to have you try these two. We'll have a Canvas quiz question here. So try these two for x, y, n, and m. The second special right triangle we're going to deal with is a 45, 45, 90. The proof of this one actually comes from a square. So I have a square here that has all four 90 degrees, but when I draw this diagonal, it becomes a 45, 45, 90 triangle. Now with a square, we know then this triangle becomes isosceles. The sides have to be the same. So I want to find what this c is, this diagonal length. So I'm going to go x squared plus x squared equals c squared. No numbers this time. But an x squared plus an x squared, that's 2x squareds equals c squared. I take the square root of both sides, and it says c equals, well, the square root of 2x squared. I can break this up into the square root of x squared and the square root of 2, or times the square root of 2. The square root of x squared is just x, and the square root of 2 we're just going to leave as the square root of 2. It's exact. But that relates it back to these other side lengths. If this length is x, this length is just square root 2 times bigger. So x root 2. So that works for any 45, 45, 90. X root 2. Not 1, 2, 3 this time. This length is then 8, and then this length is 8 root 2. And I'm done. Didn't use any Pythagorean theorem. They would have to give me this as 45. But no SOHCAHTOA, anything like that. 8 root 2. Here's two that we'd like you to try to find if given a leg, can you find the other leg and hypotenuse? And if we give you the hypotenuse, find the other legs. In 5.2.2, we had another convenience with the Pythagorean theorem. that we actually call Pythagorean triples. So Pythagoras dealing with the Pythagorean theorem, but we have a little side definition here with integers. An integer is a whole number that is not a fraction. So all those counting numbers, 1, 2, 3, 4, 5, but not 5.5 or 5.75 or any decimals from there. So Pythagorean triples are triangles where their sides consist of 3 positive integers, a, b, and c, such that the Pythagorean theorem is true. For example, let's say I have a side of 3 and a side of 4. Well, if I use the Pythagorean theorem to prove it, I would get 9 plus 16 equals c squared, 25 equals c squared. Square root that. It says c is 5, which is another integer. This is probably one of the most popular Pythagorean triples. So we have a 3, 4, 5 right triangle. So if you see on the ACT on one of our tests and they give you this side is 5 and this is 4, you don't need to do any work anymore. You just put, hey, you know what? I know this is 3, and then you move on. Done. For example, if they say this is the 3 and this is the 5, right away, boom. I know this is 4. You don't have to show any work then. We're really smart, lazy people, but I know this is always going to be true. Another example of this, one that we want you to know is a 5, 12. So if it's 5 and 12, let's check it out. I get 25 plus 144, which is a 169 equals c squared. The square root of 169 is 13. So another Pythagorean triple is the 5, 12, 13. Now, when we say we want you to know certain ones, there's an infinite amount of Pythagorean triples. I have a list down here. We want to know the 5, 3, 4, 5. We want to know the 5, 12, 13. From there, what we want to know is any multiples of these. 3, 4, 5 is a pretty common one. But if it's, like I said, a scale factor from here, if I double all these sides, a 6, 8, 10 is another really, really popular Pythagorean theorem, or Pythagorean triple. I think it showed up on one of our tests even. So we can find the multiples of these. If I triple it, it's similar by side, side, side. I just have a scale factor of 3. So these Pythagorean triples still work out in the Pythagorean theorem. So there's an infinite amount, but definitely know the 3, 4, 5, 5, 12, 13, 6, 8, 10, maybe 8, 15, 17 as an extended one from there. But definitely those first few. So I'm going to go back and show the work for those examples just to make sure you're understanding kind of the process of these. So if this is my 30, 60, 90 ratio, remember that's 1, 2, square root 3. So my short leg is 5. The hypotenuse then is always going to be 2 times bigger than that. The long leg is going to be the short leg 3, 5 root 3. It's going to be root 3 times longer. In this case, they give me a hypotenuse. But I know across from the 30, here's the short. The short leg always has to be half of the hypotenuse. So that means m is going to be the short leg root 3. I haven't touched the calculator, haven't used SOHCAHTOA, anything like that. From there then, I have 45, 45, 90 ratios. So in this case, if this is 7, 45, 45, 90, say these have to be equal. There's a 7. The hypotenuse then is 7 root 2. It's just always root 2 times bigger for 45, 45, 90s. Similar here. Now this one is a little convenient because they have this number as root 2. It's a little bit harder if it's a constant, but we can handle it. It's got to be a number root 2 times bigger. But in this case, I know if my leg is 18, then the hypotenuse is 18 root 2. And here's an 18 as well. So again, these are conveniences. We're looking for patterns that if I have a certain situation, it saves me time, whether it be on our tests, whether it be an ACT, but we don't have to show any work for these, but these ratios are going to be used throughout your math career. Hopefully this helps. We'll work on these tomorrow.